we now ask what happens if the 8 Newton force is applied at 60 degrees to the most advantageous direction. Okay, well, the most advantageous direction again is perpendicular to the moment arm. This time I drew the moment arm in the direction of the x-axis, although this whole thing could be rotated to any position and we get the same result. So the most advantageous direction is the direction of the green arrow. If we have 8 newtons at 60 degrees to that most advantageous direction, then we have 30 degrees with the x-axis, and the x component of the force is 8 newtons times the cosine of 30 degrees, or about 7 newtons. Now that component of the force is acting out this way and has no influence on rotating the hoop. Whereas the vertical component of the force, or the y component in this position, or the component that's in the most advantageous direction, is 8 newtons times the sine of 30 degrees, or 4 newtons. So that this 8 Newton force really produces only the torque that a 4 Newton force would. Because remember, the 8 newtons can be completely replaced by these two components. This component does nothing to help affect the acceleration of the hoop. This one does everything that gets done. So we have a 4 Newton accelerating force, the equivalent of 4 Newton accelerating force acting here. Now the torque in that force comes only from the component perpendicular to the radial line, which is this component, and that's going to be this. Okay, the 0.4 meters times the 4 newtons of this force gives us 0.16 meter newtons. And then the acceleration is easily found the same way as before. We divide the torque by the moment of inertia, and we get half of the acceleration that we got in the preceding problem. Now, if the system accelerates from rest through a time delta t at its in the original situation where the 8 newtons was in the most advantageous direction, we have this acceleration, 0.28 radians per second squared. Then we're going to attain a velocity, an angular velocity omega of 0.28 radians per second squared times delta t. Now the kinetic energy is going to be the sum of all the 1/2 mv squareds. Okay? And we're going to use the 1/2 mv squared, so we're going to have to find the velocities of the masses in the various hoops. Now, that means that we'll have 2 kilograms with the velocity of the hoop at 0.4 meters. Remember now, the velocity of the mass at the rim, or actually on that hoop, is 0.4 meters times the radius of the circle, which is 0.4 meters times omega, because of our relationship between velocity and angular velocity. Okay, so the 0.4 meter hoop will have this velocity, the 0.6 meter hoop will have this velocity. Actually, it's a 0.8 meter hoop and the 1.2 meter hoop. That should be 0.8 and a 1.2 meters. But they'll have the corresponding velocities, so that the 2 kilogram mass will be moving more slowly than the 4 or the 6 kilogram mass. And we'll get a total total kinetic energy. Again, we get by adding up all our 1/2 mv squareds. Now we've corrected the numbers. It's 0.4 meters, 0.8 meters, and 1.2 meters. And when we add up the 1/2 mv squared, you see we have the masses of the 3 hoops, the radii of the 3 hoops, all multiplied by the same omega because they all have the same angular velocity. What we get is 0.16 kilogram meters squared times omega squared, 1.28, 4.32, and so forth, kilogram meters squared times omega squared, for a total of about 5.8 kilogram meters squared times omega squared. Now we note that 0.16 kilogram meters squared is half of the 0.32 kilogram meters squared moment of inertia of the first hoop. Okay, so we say that that's 1/2 of, or that's I1 omega squared over 2, or 1/2 I1 omega squared. Similarly, the numbers that we have here and here turn out to be half of the moment of inertia of the second, half the moment of inertia of the third disk, so that when we add these all up, we have the kinetic energies 1/2 the total moment of inertia times omega squared. Okay? So that this makes very plausible this formula for kinetic energy, this 1/2 I omega squared, and it certainly illustrates it in the case of these three concentric hoops.